selection problem. Here the input is an array A of n numbers and an integer k between 1 and n, and the output should be the kth smallest element in A. So this is our task. Report the kth smallest element in A. So first, what is the straightforward solution to this problem? What we can do is just sort the array and pick the kth number from the left. And this algorithm will cost us n log n, because even the best sorting algorithm will cost us n log n. N log n. Okay, so n log n is possible. An interesting question is, can we improve this? And the answer is yes. In fact, we can solve this in big O of n time. We can shave off this log n. So that is linear time. All right. And the corresponding algorithm has a name. It's called the median of medians, and it's from 1973, right? Almost 50 years back. Good. So let's see what the algorithm is. What I'm going to do now is first give you an overview, then we will get into the details. So this is the algorithm. Select AK, select the kth element in A. First step is this: find a good pivot, which I'm going to call as X in A. Find a good pivot. Okay. I'll explain clearly what these things are. For now, just assume that you want to find a number in A such that A can be partitioned into A1, which is the set of all numbers in A which are less than or equal to x, and A2, which is a set of all numbers in A which is greater than x. Alright? So I just want to find a number which I'm going to call as pivot such that A can be partitioned into two arrays, A1 on the left side and A2 on the right side, such that all numbers in A1 are less than or equal to x and all numbers in A2 are greater than x. And I'm going to call this as a good pivot. I mean, I don't want just any number, I want a good number. And by good, what I mean is I want to kind of, make this partition somewhat balanced. Right? A well-balanced partition will make sure that half of the numbers or 50% of the numbers will go to one array and the remaining 50% will go to the other array. That is a well-balanced partition, but I'm okay. I can leave with, slightly unbalanced partition, but not too much unbalanced. Maybe I can have, let's say, 70% of, or at most 70% can go to one array and the remaining should go to the other array. So the exact meaning of good is something like this. The size of A1, right, and the size of A2 should be less than 0.7 n. 0.7 means what? 70% of n. That's what I'm going to call, that's what I mean by a good pivot, right? When I partition, I'm happy if I can partition 50-50. It's okay if I can partition as 60-40 is good with me. 60 on either side, I'm fine. 70 on one side, 30 on other side, I'm still cool with it. But 80 on one side and 20 on the other side, no, that is not allowed. Okay, so that's what I mean by a good pivot. And how exactly I will do this, this step, I will explain later. For now, just assume that I have a nice technique to find a number x such that I can partition this into A1 and A2 in such a way that the size of these arrays are bounded by or less than or equal to 0.7 times the size of my original array. Good. Now the next step is this. Next step, I'm coming back to my selection problem. If my k is less than or equal to A1, if my k is less than or equal to A1, what will happen is the answer which I'm looking for, that is select AK, is going to be within A1, and it is going to be exactly the kth smallest element in A1. So if k is less than or equal to A1, simply report or simply select A1 k. So I will illustrate with a small example. Suppose this is my A, and imagine n is, let's say, 100. Now I have divided this into A1 and let's say A2, where A1 has all the numbers less than or equal to x and A2 has all the numbers greater than x. Suppose A1 is, let's say, 40 and A2 is, let's say, 60. And now if I am looking for, let's say, k is 25, basically a number small less than or equal to 40, then select A25, select A25, that specific number is going to be in this array and it's going to be exactly select A125. This is what I wrote it here. So that is one possibility, that k is less than or equal to A1. The other possibility is k is greater than the size of A1. For example, k is greater than 40. Let me pick something like, let's say, 64. Then select A64 is going to be select A2. Look, here it is 64, and within the first 64 numbers, 40 has gone to the left side. So that means the 64th smallest in this array is going to be 64 minus 40, which is nothing but 16. So A2 16. In other words, this is select A2 k minus A1. Okay, and finally, whatever is output, you report. So that is a quick overview of the pseudocode or the algorithm. Okay, I hope the algorithm is pretty clear, just that some details are missing. Right? First step is find a good pivot with this condition, and once I get this, I am partitioning this array into A1 and A2, and based on the value of k, I continue in only one of these arrays. Good. So now let's see what is going to be the time complexity of this algorithm. So suppose Tn is the time to solve Suppose Tn is the time to solve the original problem, that is select AK. The first step is I need to find a good pivot, and it is going to cost us some time. I'll leave it blank for now. And once I compute that number, I need to partition this into two halves, right? Two arrays, and that step I can do it in big O of n time, that is a constant times n. Now, once I partition, the rest of the algorithm will proceed only in one of these two arrays, not in both arrays, only within one of these two arrays, and the size of that array is bounded by 0.7n. So I can write it as T of 0.7n. Alright, so this is how the recursion looks like, and I still need to figure out what is this, and that's what we're going to see next. So given an array A, how to find a good pivot so that this rules works. Okay, so let's continue. We have the recursion like T of n is less than or equal to the time for finding a good median, and once we have that median, we will split the array into A1 and A2, then continue the recursion in one of those arrays, and as long as the median is good, the size of those arrays are bounded by 0.7n. So that is how we get the next term, and finally we need to do some linear time, splitting and moving things around. Because of that, we have a Cn. Now let's see how to find a good pivot. What we're going to do is this. We'll take the array A. Let me just take a small example. A has numbers, let's say 8, 5, 12, 81, 3, 18, 36, 12, 7, 14, etc. This is what I'm going to do. I'll split the array into groups of size 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, etc. And let me call all of these as, let's say, blocks for convenience. What I will do is, from each of these blocks, I'll pick the median. Right? Median is essentially the third element in this block. So let M1 be the median of first block, M2 be the median of second block, M3 be the median of third block, etc. So M1 in this case is 3, 5, 8, the third smallest number. Here it is 7, 12, 14. Right? So just for illustration. Now my claim is this. The claim is this. X is the median of my claim is that X is going to be the median of these numbers. As we know, median is nothing but select, right? Basically select this set. I mean, if I represent this set in the form of an array, let's say M, then this is nothing but M, right? So my claim is that X is going to be the median of these numbers. So median is a special case of selection. Right, so two things we need to see at this point. One thing is how to prove that this claim is correct, and if this claim is correct, what is the time complexity for finding this. So let's do the second part first, which is, let's assume that the claim is correct. So in that case, the time for this entire process is this. First we have to split the array, find the median, and get these numbers, which can be done in linear time, big O of n time. And once we get them, it's again asking for a selection in a smaller sized array of size, how much? This is of size n divided by 5. Therefore, this step can be done in T of n over 5 plus big O of n. So let me just write it as, this part I can write as T of n over 5 plus big O of n. So that big O of n I will push to the last Cn. Okay. So all of this big O of n I will put together and write it as Cn. Alright, so now we got the recursion, and to bound the time complexity all we need to do is solve this recursion. We will do that in a bit, and most importantly we need to make sure that our claim is correct. So recall that A1 is a set of all numbers in A which are lesser than or equal to x, and A2 is a set of all numbers in A which is greater than x, right? So I want to say something. If mi, so mi is essentially the median of ith block. If mi is less than or equal to x, then ith block okay, if mi is less than the median, is less than or equal to the median, then ith block will contribute 3 elements to A1. Why is it true? It is true because the ith block will have mi, and there are going to be 2 more elements which are smaller than mi. So that means there are total 3 elements which are smaller than or equal to mi, which means 3 elements smaller than or equal to x. And when I do the partitioning, all the elements which are lesser than x will go to A1. So mi, if this condition is satisfied, will contribute 3 elements to A1. And otherwise that means if mi is more than x, then the ith block will contribute again 3 elements to, instead of A1, it will be equals to contributed to A2. Okay, and how many mi's are going to be less than x and how many mi's are going to be more than x? Since x is the median of all these mi's, the number of mi's which are lesser than x will be the same as the number of mi's which are more than x, right? And those number will be, essentially it will be split into half. Since the total number of mi's is n over 5, exactly n over 10 mi's will be less than or equal to x and n over 10 will be more than x, and each of them contributes 3 to A1 and each of the other ones will contribute 3 to A2. That means what we can say is, at this point, is the size of A1 is greater than or equal to 0.3 n. Similarly, the size of A2 is also greater than or equal to 0.3 n. Okay. Now, the size of A1 greater than 0.3 n implies the size of A2 lesser than 1 minus 0.3, that is 0.7 n. Similarly, the size of A2 greater than 0.3 n implies the size of A1 is also 0.7 n. So we are done. That's what we wanted to get. So we managed to prove that the sizes of A1 and A2 are bounded as we wanted. Therefore, X is a good pivot. So the entire algorithm will work, and this is the corresponding recursion. So all we need to do now is just focus on this recursion and show that this is big O of n. Okay, so now we are here. I just need to prove that this recursion is equal to big O of n. Okay, so normally when you have recursions like this with different terms on the right side, a direct expansion might become too messy. So we typically use another method called substitution method. Substitution method for solving recursion. The idea is this: make a good guess about Tn, then prove that your guess is correct. So guess means what? It is a hypothesis, right? So guess or a hypothesis. And you prove that your guess is correct. And what we're going to use is nothing but mathematical induction. This is what I'm going to use. Okay, so I need to make a good guess first. So let me guess that T of n is less than or equal to, T of n is big O of n. That means T of n is less than or equal to some constant. I'm going to use B times n. So that is my guess, and I need to prove that my guess is correct using mathematical induction, or this relation is correct using mathematical induction. All right. So I'm going to assume that this is true for, for some value of k. For some k, I'm going to assume that this is true for 1, 2, 3, 4 up to k minus 1. So that means T1 or T of some constant is less than or equal to B. T2 is less than or equal to 2B T. K minus 1 is less than or equal to k minus 1 times B. That's what we do in recursion, right? Now I need to prove it for, prove that this is true for Tk, and you exploit this relation. So what is Tk over 5? I'm just writing the right side. What is Tk over 5 plus T 0.7k plus Ck? This is, using that relation, I can write as less than or equal to you see that these are numbers. What is inside is less than k, what is inside is less than k. So I can substitute these values. So this is nothing but 1 over 5 is 0.2 bk plus 0.7 bk plus ck, which is equal to 0.9 p plus c times k. Okay, And now if I fix the value of, let me fix b is equal to 10c. Okay, if I fix b is equal to 10c, what will happen is, if you evaluate what is inside, this will become basically 9c plus c, that is 10c. 10c is equal to b, so that is bk. Okay, so what we have just proved is this. What we have just proved is this: the right hand side, the RHS is less than or equal to bk. Okay, and we know that the LHS, or the RHS, the right hand side, is less than or equal to bk, and we know that the left hand side is anyway less than or equal to tk. Now if you read these two things together, tk is less than or equal to bk, so that means tk is less than or equal to bk, and which means using mathematical induction we have proved Tn is less than or equal to Bn, or the whole thing is big of n. Yeah, you don't need to do all these things in so detail. I mean, I just showed it, using baby steps, but yeah, this could be made much faster. Okay, this could be simplified a lot. Anyways, so this is how we prove that the running time of our algorithm is linear. Okay, so before I stop, I just want to say a couple of more things. One is, sometimes people wonder why did or how this number 5 was chosen, right? We chose the block size as 5, and what is the reason? Or can some other number works? Okay, so remember you have A, right, and you are blocking by 5, and that's how we got this 5. And whether another number will work, my answer is yes. For example, if I pick 7, this inequality will look like Tn is less than or equal to, instead of n over 5, this will become n over 7, and the second one will become T of, this 0.7 we got this way. 0.7 we got this as 1 minus, on top you should have 3, on bottom you should have 2 into 5. That is how we got 0.7. Now if you use 7, this will become 1 minus 4 divided by 2 into 7. This is, this will be like what? 2 by 7, that is 5 by 7. So 5 divided by 7, n plus Cn. And if you expand this and if you solve for this, you will again get big of n. And if you try with 9, that is T n divided by 9 plus T. With 9, this will be, the numerator will be 5, and you will have 2 here, the 9 here, so that is 18 minus 5, which is 13 divided by 18. So 13 divided by 18, n plus Cn, and you can try it by yourself. This is also going to be O of n. So in general, you can pick any number, any odd number which is greater than or equal to 5, and the time complexity is going to be linear. The reason why 5 was chosen was there are like many hidden constants, and that is the constant is going to be the smallest when we pick 5. That is how 5 was chosen. But what if we choose 3? If you choose 3, the recursion will look like this. Okay, let me just choose 3 and see how it's, just for the sake of completeness. Okay, so what I really want to prove is this quantity. Basically, I want to make a good guess that Tn is less than or equal to Bn. For that, I assume this is true for 1, 2, 3, 4 up to k minus 1, and when n is equal to k, the right hand side will be n over 3 into b plus 2 times 2 over 3 nb plus cn, right? And this will become bn plus cn. And what we really wanted is less than or equal to bn, which unfortunately is not true. That means our initial guess of t of n less than or equal to b of n is not true. So in summary, the sample size of 3 or the block size of 3 will not work. We need to pick at least 5, and picking 5 is the best in terms of minimizing the value of the constant or the hidden constants. Yeah, so that is the end of linear time selection.